for today's lesson, we will be discussing about continuity of a function at a point. So we will be discussing what does continuity mean and when can we say that a function is continuous at a given point. So before we proceed with the discussion, let's recall first the limits. So as what we know, limits, this is the value that the function approaches as the value of x approaches a certain number. And there are cases wherein we can use direct substitution in order for us to identify limits. So let's try to solve here some examples and let's try to identify the limits. So let's say we have limit of x minus 2 as x approaches 2. Since this one is an algebraic expression, so what we can do is we can just do direct substitution. So this will be 2 minus 2, which is equal to 0. So therefore, the limit of x minus 2 as x approaches 2 is equal to 0. Again, we only use direct substitution since this is an algebraic function, and we discussed this last time that when we have algebraic functions, or let's say this one is a polynomial, so we can just do direct substitution, or we can say that the limit of the function is just the same as the f of c. So we can also solve for f of c, or f of 2 in this case. So we have 2 minus 2, which is equal to 0. So they are just the same. So limit of our f of x as x approaches c is just equal with f of c. So another way on how we can check the limits is by using the graph. So let's just look at the graph of this function. So this is the graph of the function f of x equals x minus 2. So as you can see, it's just a straight line, and we have this point here. As you can see, this 2, this one is shaded because if x is 2, then we have a value which is 0. So technically, 2 is part of the domain of our function. And to solve for the limit of the function using the graph, you can just observe the function from the left side of the x and also from the right side. So this one and this, and they're just going to the same number, which is in this case is 0. So in this first example, we can see that the limit is just equal with f of c, and by substitution we're able to check and see that the value of c, which is 2, is really part of the domain of our function. Let's have another case here. Let's say we have limit of x squared minus 4 all over x minus 2 as x approaches 2. So this one, this is also an algebraic function, particularly rational function. And like what we did last time, whenever we have rational function, we can just substitute again. But if we will substitute, what will happen is that we will get 2 squared minus 4 all over 2 minus 2, which is indeterminate. So we cannot use direct substitution because what will happen is that it will become indeterminate. So what we can do is we can simplify this one first. So we factor. So we have x plus 2 times x minus 2 all over x minus 2. And then we can cancel the x minus 2, so we will be left with x plus 2. And from here, we can now get the limit of x plus 2 as x approaches 2, which will give us 2 plus 2 or 4. So the limit of our function is equal to 4. Now, if we will just get f of c or f of 2, so like what happened in the first part of our solving here, if we do substitution, what will happen is that we will get an indeterminate. So 0 over 0. So this means the limit of our function this time, f of x as x approaches c, is not equal with f of c, because we're not actually able to get a value for our f of c. It's indeterminate. Now what does it mean? If we will look at the graph, so this is the graph of our function. So this is f of x equals x squared minus 4 all over x minus 2. So this is the graph of our function. Now, at this point right here, you can see that there is a hole. So we have here unshaded circle This means that whenever the value of x is 2, we cannot get the corresponding value of y. Because like what we did here, as we substitute 2 to our function, it becomes indeterminate. That only means that c is not part of the domain of this function. Since c is not part of the domain of the function, when we graph this, so there should be a hole in this part right here. Okay? But if we will get the limit, so again, just look at the left and to the right side, so they will go to a value of 4. So there are cases wherein the limit of the function is the same as with f of c. There are also cases wherein they are not equal, and when we graph it, we can see that there's a hole in our function. Now, these two examples leads us now to what we call as the continuous function and also the discontinuous function. So let's define first what is continuous function. So a function is said to be continuous if its graph has no breaks or holes and you can trace it without lifting your pen. A continuous function is defined for any real number. So as like what you saw here, has no breaks or holes and you can trace it without lifting your pen. So in our previous examples, if we will go back to it, so the first example, as you can see, there are no holes. So there is a corresponding value for each value of x. But for our second example, so as you can see, if we'll just go back to this, you will see that there is a hole here at x equals 2. So that means the function breaks at this point because 2 is not part of the domain already. So that is not continuous. And another thing is that you can trace it without lifting your pen. And a continuous function is defined for any real number. So what do you mean by defined by any real number? So that means all of the values or all of real numbers can be used as the value of x or is part of the domain of our function. So whenever you substitute any value to your function, you will get a particular value. So this is an example of a continuous function. So as you can see in the graph, there's no hole. So we have this point right here, but this point is actually shaded. So that means 2 is still part of the domain because if we substitute 2 to our function, this is the example a while ago. If you substitute 2, so we will get the value of y, which is 0. So there's no breaks or holes here. And then you can also trace it without lifting your pen. So you have to do, let's say you start here, so you can trace it continuously. So you will not stop at 2 because 2 is part of the graph. And then there you go. So that is an example of a continuous function. So let's have more examples of continuous function. Okay, so let's say we have here f of x equals x squared. So this is an example of a continuous function. So as you can see, you can trace it without lifting your pen. So there, you can trace it without lifting your pen. And our function is defined for any real number. So if it is defined for any real number, that means there will be no breaks or holes in our graph. So you can use any value of x that you want and you will still obtain a particular value. So therefore, this function is continuous. Another example, let's say we have f of x equals 2x plus 5. So again, you can trace it without lifting your pen. And again, there's no hole or there's no holes or breaks or gap between our graph because this function is defined for all real numbers, meaning any value of x will give us a corresponding value of y. And last example is sine of x. So the function of sine is also continuous. As you can see, I can trace it without lifting my pen. And as what we remember with sine, the domain of it is set of all real numbers. So that means sine is defined for all of real numbers. So that means there will be no breaks or holes into our graph. Now, the opposite, of course, of continuous function is what we call as discontinuous functions. So when can we say that our graph or the function is discontinuous? Of course, if there are holes or gaps or breaks, and if you cannot trace it using your pen without lifting it. So let's see some examples. Let's say I have f of x equals absolute value of x over x. So this is an example of a discontinuous function. First, I cannot trace it without lifting my pen. So I will start here. So I will trace this, but I need to stop here. The second part of the graph is above this one. So I have to lift my pen and then move here to continue. So since I was not able to trace it without lifting my pen, that means this graph is discontinuous. That means there are gaps between our graph. And as you can see, this function is not defined for all of the real numbers. So there's a restriction. For example, 0. If x is 0, then this will be absolute value of 0 all over 0. So that will be indeterminate. So that's why we have whole here, because 0 will not give us a value of this function. So another example is this one. So I have here a piecewise function. So again, I cannot trace it without lifting my pen. So I will start here, then I need to stop at this point, and to continue I have to jump or go here and then trace it again. So again, this is an example of a discontinuous function. And last, we can also have this kind of graph. F of x equals x minus 1 all over 2x squared minus x minus 1. Although there are no holes here in our graph, but as you can see, there is an asymptote. Okay, so that is also considered as division between our graphs. So I can trace it without lifting my pen on this part, but I have to lift my pen if I want to trace the other part of the graph. So these are examples of discontinuous function. So all you have to remember is that for continuous function, first is there should be no breaks, no holes or gaps in between, and you can trace it without lifting your pen. And the function should be defined for all real numbers. And then the other way around is what we call as the discontinuous functions. Now, when can we say that a function is continuous at a certain point? So a function f is said to be continuous at a number c if and only if the following conditions are satisfied. So when we say a function is continuous at a certain point, we're going to check if it is continuous, or will there be a hole at that point, or is that particular value of x part of the domain, and so on. So in order for us to determine, so these following conditions must be satisfied. First, f of c exists. So that is the first thing that should be considered. F of c exists, meaning if you substitute c to our function, we're able to get a particular value. Next, the limit of f of x as x approaches c exists as well. So after checking the value of the function, if x is c, we also have to identify the limit and check if it exists. And lastly, the limit of the function must be equal with f of c. Okay, so these three conditions must be satisfied. So first, f of c exists. Second, the limit exists. And the third one is that the limit and the value of f of c must be equal with one another. If at least one of these conditions fails to hold at c, the function is said to be discontinuous at c. So what do you mean discontinuous at c? So maybe there is a hole at that value, or the graph breaks at that particular value, and so on. Now let's determine if the following functions are continuous at a given point. So first, determine if f of x equals 2x squared minus 6x plus 2 is continuous at x equals negative 3. So all we have to do here is to solve for first f of c. So since c is equal to negative 3, so we have f of negative 3. So let's just substitute. So that is 2 times negative 3 squared minus 6 times negative 3 plus 2. And then let's simplify this. So we have 2 times 9, that's 18, plus this one will be 18 as well, plus 2. So we have 38 as our answer. So 38 now is the value of f of negative 3. Now after that, let's solve for the limit of our function. So the limit of 2x squared minus 6x plus 2 as x approaches negative 3. Now, since what we have is a polynomial function, so to identify the limits, we can just do direct substitution. So this will become 2 times negative 3 squared minus 6 times negative 3 plus 2, which is just the same as the value that we obtained a while ago. So this will be 38 as well. Now, since we notice that the limit of our function f of x as x approaches negative 3 is the same as with f of negative 3, therefore we can say that the function f of x equals 2x squared minus 6x plus 2 is continuous at x equals negative 3. So this will be our conclusion. Again, we can say that the function is continuous because after solving for f of c and the limit of our f of x, we're able to see that they just have the same value. So it is continuous at the given point x equals negative 3. Another example is g of x equals 2x minus 3 all over x squared plus 4x plus 4 continuous at x equals negative 2. So first, let's try to solve for g of c. This time it's g of negative 2. So let's substitute 2 of negative 2 or 2 times negative 2 minus 3 all over negative 2 squared plus 4 times negative 2 plus 4. Now let's simplify this. So 2 times negative 2 is negative 4 minus 3, so that's negative 7. And the denominator will be 4 minus 8 plus 4, that will give us 0. So after substituting negative 2 to our function, what we obtain is an undefined. So this one now is undefined. So what does it mean? This means now that g of negative 2 does not exist. Now, since g of c does not exist, it already violates the first condition, which is f of c must exist. So there's no need for us to continue this because in the first condition, it's not already satisfied. So since this function failed to satisfy the first condition, which is f of c must exist, then we can say that the function g of x equals 2x minus 3 all over x squared plus 4x plus 4 is discontinuous at x equals negative 2. Although you can also say the function g of x is not continuous at x equals negative 2. Okay, so this will be again our conclusion, since the function failed to satisfy the first condition. And then for our last example, so let's say we have here this one. H of x is a piecewise function, and we will check if it's continuous at x equals 3. So first is we will solve for h of 3. So this means we have to substitute 3 to our function. But since this one is a piecewise function, so we have to choose which among our sub-functions should we use. Since it's equal to 3, so that means we will be using the second sub-function. But since our second sub-function is a constant function, so whatever value of x that we use, it will still lead us to the same value, which is 0. So therefore, h of 3 is 0. So this is now the value of our function if x is equal to 3. Next, we have to solve for the limit. So limit of h of x as x approaches 3. Now, since we're going to solve for the limit, so that means we have to consider the left-hand limit and the right-hand limit. So let's just write here first, limit of h of x as x approaches 3 from the left, and we will also solve the limit of h of x as x approaches 3 from the right. Now, we have to choose which among the sub-functions should we use for each side. So first, x approaches 3 from the left. So when we say 3 from the left, so let's say this is 3 and then this is the values of x from the left, that means those values are less than 3. So we just have to choose which among the 3 sub-functions should we use, since what we will be considering are the values less than 3 or the values from the left of 3. So we will be using the first sub-function. So this should be limit of x squared minus 6x. So x squared minus 6x. So we just have to substitute. So this is now 3 squared minus 6 times 3. So this is 9 minus 18, or this is negative 9. So this is now the limit of our function as x approaches 3 from the left. Now we have to look at the limit of the function as x approaches 3 from the right. Now if we're looking at the values of x from the right of 3, that means what we want are greater than 3, or values of x that are greater than 3. So therefore, we will be using our third subfunction, which is 5x plus 3. So we have here 5x plus 3, so substitute 5 times 3 plus 3. So this is 15 plus 3, or we have 18 as our answer for the right hand limit. Now, you just have to look at the left hand and the right hand limit, check if they are equal. But since they are different, one is negative 9, the other is 18, that means we can say here now that the limit does not exist. Why the limit does not exist? Because the limit will only exist if the right hand and the left hand limits are equal with one another. Now, as we can see here, we have h of c. It exists. The value is 0. But for condition number 2, when we check for the limit does not exist. Since it failed to satisfy the second condition, that means our function is still discontinuous at the given point. So we have to write here the function h of x is discontinuous at x equals 3. Or the function h of x is not continuous at x equals 3. So that's it for today. I hope you learned something about continuity of a function. When can we say that a function is continuous or not? And when can we say that a function is continuous at a certain point? And see you next time.